So disaccharides are simply made up of two sugar units. So we are simply going to be combining two monomers, two sugar units of monosaccharides. So two units, so two sugar units will make up a disaccharides. That's one thing you need to know. Then another thing you need to take note of is that these sugars are going to be combining in a reaction that we call a condensation reaction. So a condensation reaction, or rather a dehydration reaction. So we call it a condensation or dehydration reaction, will produce a disaccharide. This is going to be illustrated if I give you a glucose and a fructose molecule. So I'll just write it quickly here. So what we mean by a dehydration reaction, we just mean that when these two guys combine, there's going to be a contribution of the hydroxyl group from the glucose and the hydrogen group from the fructose. So this is, let's say this is our fructose. So dehydration just means the removal, or rather the production of water. So if we have this, something like this, so the final thing, these are two monosaccharides, two units of two monosaccharide units. When they react, they will simply produce a disaccharide, and the bond that is created between them is called a glycosidic bond, and it's going to be named after the carbons that are participating in the bond. So we have what you call the 1 and 2, 1,2. So the carbon that we are using in this, I want to write the byproduct. So this carbon that we are using, so on oxygen we needed to, on the glucose, I needed to write something that looks like this. There need to be something like this. It was supposed to be like this. There's a carbon here which is holding these two guys, the same way that there's a carbon this side. So this is the first carbon. This guy here is the first carbon. It's bonding or relating with, this is 1, 2, 3, 4. This is it 4, 2? It's supposed to be 2 because on the fructose it's arranged in such a way that the first carbon is here on top. This is 1, this is 2, 3, 4, then 5. So now we are saying the bond that will be created will be called a 1,2 glycosidic bond, because it's a relation between the first carbon and the second carbon on the fructose. So dehydration produces a disaccharide, and the reverse is simply called hydrolysis. So hope you've done that, you've seen that in class. So they put something like this. So going like this, it's dehydration, or rather condensation, the production of water. Then going back, or rather we are saying we can break down the bond which is created between the two. So this is what you are creating between the two molecules, something like that. And you are having, there's a hydrogen there. This is giving us something like this. So this bond that is created here is what we call the glycosidic bond. And when you add water, and also water is a byproduct, when we add water, we'll simply break down your disaccharide. So your disaccharide can be broken down to create the monomers that we initially had. So this is the first thing you need to take note of. Then the first common disaccharide that we're going to be discussing, or the structure that you need to know, when you combine glucose and fructose, you produce the first type of the common one, which is sucrose. So sucrose is just a combination of a glucose molecule. So you have glucose plus a fructose molecule. So this is alpha glucose or N, depending on the isomers that you are using. So hope you remember the isomers, the D and the L, right? The dextro and the levo isomers that we explained in the first part. Yeah, so whatever you use, we're just saying whenever you combine a glucose molecule and a fructose, whether it's alpha glucose or beta glucose or D glucose or L glucose and a fructose, you always produce a what? A sucrose. That's what you have. And because it's a disaccharide, sucrose is a non-reducing sugar. Anyone, guys, to explain to us what a non-reducing sugar means? What do we mean when we say it's a non-reducing sugar? So it's a non-reducing sugar because it contains, this is because it contains a ketone part from the glucose. So it has a keto part and an aldose part. Yeah, so I did explain in the first video I sent what we mean by having a ketone and what we mean by having an aldehyde. Yeah, so because of these two properties, we're always going to be having sucrose as a reducing sugar, because the practical illustration is how it's used in industries as a sweetener, in terms of, let's say, for baking, as a food preservative in some industries. Yeah, so this is what we have. If you are interested to talk about a ketone or anything that exhibits a ketone properties or ketose properties, you see that the carbonyl group, this guy is squeezed between two alkyl groups. So there could be anything this side and there could be anything this side, but what is bonded or what is squeezing the carbonyl group should never be attached to a hydrogen. So we're saying whenever the carbonyl group is squeezed between two other carbons, meaning it's a what? It's a ketone. Then if it's an aldehyde, we say one part of the carbonyl group is attached to hydrogen, the other part is attached to a carbon or anything else, but not a hydrogen, only one hydrogen. Now, what we mean by sucrose being a non-reducing sugar, because it lacks a free aldehyde or ketone group, preventing it from acting as a reducing agent in chemical reactions, unlike reducing sugars. So, if something has a free ketone or aldehyde, meaning it can reduce the sweetness of something, like this guy is a non-reducing sugar, meaning it's like it increases the sweetness of something. No wonder its practical applications, or where this guy is found, is in bakeries, or rather in sweeteners, sometimes in food preservative. That's the only time we can have sucrose being used in domestic things. Yeah, so in simpler terms, what we mean, John, when we say it's a non-reducing sugar, scientifically we're just saying it has no, so let me just indicate this, contains no free ketone or aldehyde group. Yeah, so it does contain them, but then they're just not free, they're being used up. Yeah, if it had free aldehyde or ketone groups, meaning it will have the ability to reduce other things, meaning things can be able to be attracted or rather react with it. This is why disaccharides are very important, because it takes time for you to hydrolyze them, to break them down. So if we store your energy or your biomolecules that you consume in terms of sucrose, we can always break them down under cellular respiratory activities to break them down back to glucose and fructose whenever they are needed. Yeah, so this is a better form of storage in terms of energy as compared to monosaccharides, because these are a bit complex. Yeah, hope that answers your question, John. What we mean by non-reducing sugars. Is this okay?
Yes.
Okay. The second type of, the second common monosaccharide that you have to know is simply lactose. This is also known as milk sugar. So this has, the domestic name is milk sugar. So what biomolecules make up lactose? What two monosaccharides do we need to form lactose? Guys, you've been studying this, you just started learning this. So what two monosaccharides are needed or should be added to produce lactose? So this is just galactose and glucose. So when you add galactose and glucose, you produce, so you have to know the patterns, right? Sucrose, we said you have glucose and fructose. Lactose, you just need what? Galactose and glucose. Glucose and galactose. And the bonding should be the same, but it's going to create a 1,4 glycosidic bond because of how the structures are made up. So this will do it our time, but I'll just sketch the diagram here. So you have your galactose that looks like this. So just draw the skeletal structure just to indicate the glycosidic bond when we're done. Also, this will be formed through the same dehydration or condensation reaction. Then you have your glucose on the other side. Yeah, so I'll put our glucose there, something like that. Then here I'll just have your hydrogen. Then you have the other guy here, which is your hydroxide. So you have your galactose here, something like that. Then you have your glucose there. So we're saying when these guys combine, so this is important because you can have something that looks like this. We actually do it, pair it in the opposite way. So we can have a situation where we contribute, we get one hydroxide from here, and we also get one hydrogen from the other side, something like that. Yeah, so that we remain with hydrogens on both parts. So this will create something that will be like a zigzag glycosidic bond. Yeah, so it will be, this will be that. And then you have this structure. This will create something that looks like that. We have the oxygen here that remains bonding to the other carbon here. So this will just be drawn like this to show, to say we are having something like that. Then there will be a hydrogen there, and there will be a hydrogen this side. So this is the type of glycosidic bond that you will see in a lactose molecule. And the name, they always get specific about this. This is always going to be a 1,4 because we're using carbon number 1 from the galactose and carbon number 4 from the glucose. We start with a smaller number. You cannot say 4,1. We always start with 1,4 glycosidic bond. Any question, guys, here so far? We're just saying this is the second common disaccharide, which is lactose, formed by these two guys, and it's still going to be a condensation reaction to produce it. And to retrieve them back, to retrieve the monosaccharides, you still have to add water. Water is a byproduct of the condensation reaction. Yeah, so hydrolysis, the addition of water will get us back to the monomers. Yeah, so the formula is just going to be the addition of galactose and glucose minus water. So you have this is just for your learning basis, but they'll never ask you this. So your formula for lactose will just be C12H, then you have O11. This is what you have. So now here we are saying this is a reducing sugar. So some properties you need to know about. So we say properties of lactose. This is just going to be a short list, and the first one is that this is a reducing sugar. So now you can just say the opposite. Now, what do we mean when we say it's a reducing sugar? I gave you a definition of what a non-reducing sugar means. What does this mean when we say it's a reducing sugar? What do we mean, guys, when we say it's a reducing sugar?
It means there's a free ketone group.
Yes, it just means what we said. A non-reducing sugar has no free keto group. So this guy has free either a ketone, a free keto group, whether a ketone or an aldehyde. It has free plenty of these groups, so that when we add it to something like this, is a practical illustration, is that once extracted, from wherever we are getting it from, let's say from milk, because we say this is the domestic name is milk sugar. So it's the practical illustration is that this guy is added to beer in some beverages to reduce the bitterness. So it reduces the bitterness because of the free groups that you have. So reduces the bitter taste. So this is the industrial one of the industrial applications of this, and it's a source of energy in tissue respiration because we can easily break it down to formulate back the galactose and the glucose. So now when you say someone is lactose intolerant, what do we mean? What do we mean, guys, if we say someone is lactose intolerant? Guys, you've heard people say they don't take milk, right? What do we mean when you say someone is lactose intolerant? Daniel, John, what do we mean? So we basically just mean that this person cannot digest the biomolecule, in this case the same milk sugar, or rather the lactose. In actual sense, or rather in simpler terms, we can just say they lack the lactase enzyme. Their body cannot produce lactase, so lactose is always broken down by the enzyme lactase in mammals or in animals to produce back the galactose and the glucose for us to have energy, the tissue respiration, the energy activities, for us to derive energy from these biomolecules. So whenever they lack this, so sometimes it causes coagulation. Most of them have reactions, right? You see why it will either pop up in terms of maybe their skin, or rather some sweat, some try to the nausea feeling, whatever symptom that their body will dictate to say they've taken something that their body cannot welcome or digest. The biological reason is because they lack this enzyme. The body cannot produce this enzyme to digest it. So it signals via this the symptoms that they exhibit. So when you say someone is lactose intolerant, meaning they cannot just digest it. So this is what we have as one of the disadvantages of these biomolecules. And the last common disaccharide that you have to know is maltose. So maltose, this is also called malt sugar. That's the other name, the common name. So I should have mentioned to say this guy is also soluble in water, right? This guy, one of the properties is that this is soluble in water. The reason why it's soluble in water is because you learned underwater say water is dipolar, right? So it can always create those minimal dipole moments to force something to dissolve in it. And because these guys contain a lot of hydroxyl groups, that's the other reason why carbohydrates, if not all, most of them dissolve in, or they are soluble in water. So maltose is going to be a byproduct of two glucose molecules. That's what produces. So here we just have to add two glucose molecules. So glucose plus glucose will produce maltose. That's what we're basically saying. So this is mostly produced by the digestion of starch. That's the main production of maltose is whenever starch is being broken down, and the enzyme that is always used to break this to break maltose into the two glucose molecules is we just change the prefix. So we'll just say it's maltase. That's the enzyme that is needed to break maltose into two glucose molecules. And it will also create a 1,4 alpha glycosidic bond, because the two glucose molecules we'll be using will be alpha glucose, alpha glucose. So we're going to produce a 1,4 alpha glycosidic bond. So by now, I did explain in the first introduction what we mean by alpha and beta. The location of the hydroxide group, if it's down, meaning it's alpha. If it's above, meaning it's beta. That's basically how we identify it. Yeah, so you know how glucose looks. Now we're just saying we are combining two of them. There's one glucose here. Yeah, so there's one glucose there. This is this. Yeah, so this is, this has to be, the oxygen has to be here on top. Something like this. Yeah, so this is carbon 1, 2. Then with regards to the other glucose molecule that we're using, the oxygen will still be here and everything is still intact. You notice that we're using, this is 1, 2, 3, 4. So we're using the first carbon from the first glucose and the fourth carbon on the second glucose. That's where the 1,4 is coming from. And both of these guys at the hydroxyl group is at the bottom, because here you see something like that. At this point you see a hydrogen, the hydroxide is down. So even this is alpha. No wonder we are creating a 1,4 alpha glycosidic bond. But the reaction is still going to be that we are combining one hydroxide and this hydrogen here, so that the glycosidic bond that will be created will be looking like this. Yeah, so it will be simply looking like that. There's a hydrogen there, then yeah, something like that. Then you have, yeah, so something like this. Yeah, so this is going to be the alpha 1,4 glycosidic bond. That's basically what we have. And this is the, yes, Macnon?
Are you presenting, because we can't see the screen?
Oh, you can't see
the screen.
Oh, yes, I am. It's still presenting. Let me, okay. Let me just reload it. You're able to see it now, right?
Yes, sir, we're able to see it.
Okay, so, okay, at least, but I've recorded it. Okay, so let me just scroll down a bit. And the common application of this is, this is an intermediate, because remember the common one that humans always use, or even if we talk about cellular respiration, we always talk about glucose, right? The burning of glucose to produce energy in form of ATP and everything else. So now, this guy is said to be an intermediate, yeah, something that we have in the production of other things like, let's say, fermented beverages. This comes, let's say, a typical illustration is maize, right? Maize is a perfect example of a carbohydrate, and in things like cereals as well, you see it in millet, in rice. So those are just like quick things that our bodies can digest, because it's the same thing repeating itself in a network of glucose molecules. Yeah, so that's basically what you have. So this is simply a breakdown of the important disaccharides that you have to know. And also, maybe if I may emphasize, you also have to know the enzymes that give us these things. So the carbohydrate, if we talk about starch, for instance, so this is me summarizing this now. So if we talk about starch, for instance, the enzyme that you need to break down starch is simply amylase, and it produces maltose. Yeah, so maltose is an intermediate or a simpler form of starch. So when you have starch, you can break it down to maltose, and we know here we use amylase. And you know that this guy, again, via a hydrolysis reaction, can give you two glucose molecules, right? So here we're saying two glucose molecules plus another what? Plus another glucose molecule. The same applies to maltose. Maltose. We're saying not only can you use water to break it down, you can also use maltase, the enzyme maltase. Just change the OSE, just put ASE. Yeah, so it will give you the name of the enzyme that breaks down that particular disaccharide. Yeah. So we discussed about lactose, then sucrose. The enzyme that breaks it down is sucrose or invertase. Then you get your glucose and your fructose. Yeah, so this is simply a partial summary of disaccharides. The next time we discuss these disaccharides is when we are wrapping up, or rather when we are looking at the last part, which is polysaccharides, because from monosaccharides, we are combining the monosaccharides, we created disaccharides. Now we're going to combine these disaccharides and then create polysaccharides. For example, starch, though I've mentioned here, it's a polysaccharide, an intensive network of maltose molecules, which can be broken down to create the monosaccharides, making it up, which is glucose. So a network of glucose molecules, when there are more than 3, they will create a polymer, or rather a polysaccharide, which is going to be very heavy or very dense with unique properties. Yeah, making it a little bit less soluble because it's in a very packaged state. Yeah, so hope this is okay.